Go. So this is AKA the vector product. Are you guys? Any of you guys familiar with the cross product?
No.
No.
I've heard it before.
I've heard words.
I've heard you said something about it and then said, but you don't have to know that.
Okay. So the cross product, first of all, if you have a vector, this is only works for vectors in space. Okay, so geometrically, what the cross product is, we read this A cross B. Okay? What the cross product is you take two vectors and you cross them, you multiply them, and the result is a third vector. And that third vector is a vector that's perpendicular to both A and B. Okay? So, like, if you're looking at this right here, what I've just drawn, there are two vectors that A cross B could be in our minds right now. A vector that's perpendicular to this vector A and a vector that's perpendicular to this vector B. Like, which direction would those point?
This way.
Yeah. So either towards you, like, you know, that way, or towards me, this way. Okay? So we have to sort of reconcile that because A cross B we want it to equal one thing, not two things. And so the convention is what we call a right-hand rule. And so the way that you can figure out which direction A cross B points is you take your right hand. Okay, now this is...
Or you do this.
Yeah, or you do that. And this is backwards for you because this looks like my left hand, like on the screen, right, for you guys?
Yeah.
You take your hand and you wrap your fingers from your right hand from A to B. So you wrap from A to B, and then my thumb is now pointing in the direction of A cross B. So it's going to point towards you. So A cross B would point towards you, okay? And then I'm gonna make that not dotted. I'm gonna make it a solid color.
Wait, what? Mine? Can you do the hand wrap again? Because mine went away.
I went towards.
Towards you?
Yeah, like, so if I put my palm, like, where A is, and then I curl around the rest of my fingers, my thumb's pointing out, which would be towards me. It's just
With
I
your
can't,
right hand?
Yeah, with my right hand.
I don't know if I'm dumb or something. But wait, which way did you go? Like inside or outside? Like
I don't know what you mean.
You have to so, and this is really this didn't even dawn on me that this was going to be so like complex in a two-dimensional space. Like this is so much easier when you're like next to me and I can like show you in 3D. Like you have to you curl your fingers from the one that's first to the second one. So if I'm going to curl my right hand from A to B, like from A to B, that's how it's going to point in towards the wall.
Since I drew mine like you drew yours, and since it looks like you're doing it with your left hand, like my A is going around the outside.
that's what. Okay, yeah.
Yeah,
So
that's
does it
what
go
I do.
like 270 degrees or 90 degrees?
It goes 270
You don't
degrees.
wrap your hands like this and point out.
That's the only way mine can point towards me.
Yeah, because ours
Sorry.
are.
Right. So, I got you. It's we're not. I just when I say towards you on your paper, it's going to point into the paper, not at
Oh
you.
my gosh. Okay, I had it right.
Yeah.
I'm not dumb. Jeez.
Like mine, when I say towards you, you're on the other side of this glass wall in that camera. So when I say towards you, like it's pointing into towards the camera. Like
Oh boy.
yeah.
Okay,
Okay.
I gotcha.
So that's A cross B, like and then B cross A is going to point this way. It'll have the same magnitude, but B cross A is going to point in the opposite direction. Okay? Does that make sense?
Yeah.
And honestly, we're
Yeah.
not gonna get into too much where this right hand rule is going to become a major thing. I mean, it will a little bit down the road, but by then, hopefully, you're going to be sitting in front of me and we can fix it. Okay, so you ready? So how do we compute this is now the question.
You
Bless you.
multiplied the x and y values to the opposite ones, I think. Shoot, I forgot about z.
Yeah, remember, this only works with vectors in space. Okay. Well, you can cross two vectors that are in the plane, and the cross product. Well, actually, I'm not going to tell you that. I'm going to test you on that in a minute. So here's two vectors that we've defined: A1, A2, A3, B1, B2, B3. Okay. And then we're going to say A cross B. Okay. Now, if you take Physics 2, or if you've taken, if you're in Physics 2 now, who's in Physics 2 now? Emily and or just all of you. Oh, so I'm teaching you this before McManus is teaching you this, which is a rarity. He's going to just teach you an algorithm on how to compute the cross product, like just a formula. I don't have that formula memorized. How I do it is actually by computing what we call a 3x3 determinant. Okay? Now,
Okay,
maybe
hold
after
on,
you-
I gotta draw this.
Maybe after you learn McManus's kind of formula, you won't like this determinant method. I just like this determinant method because I know how to calculate a 3x3 determinant, and I don't have to memorize a formula. I mean, anytime I don't have to memorize something is better in my life.
We have to memorize how to solve it.
Well, you have to memorize how to calculate a 3x3 determinant, because I'm guessing you don't. Do you guys even know what a 3x3 determinant is?
I think we did something with them last year, but I don't really
Yeah,
remember.
you probably did something with determinants. In Algebra 2 would be the first place that you would have seen it. I mean, a determinant is basically
a big parenthesis. I don't
It
know.
looks like a matrix of us.
right.
Yeah.
But okay, Snyder was like, you'll probably be able to figure out the matrix.
Okay, so
Yeah.
this. Okay, now just listen. This right here is a matrix. Okay, this is what we call a 3x3 matrix. 3 rows, 3 columns. Okay, that's a 3x3 matrix. Okay, matrices are used all over the place. Okay, I mean it's a very, very major thing that you probably should learn about in Algebra 2. But you just have so much other crap that you have to do. One place that matrices are probably introduced is when you're doing systems of linear equations. So like this matrix may coincide to a system of equations or a system of things like 1x plus 2y plus 3z, 2x plus 1y plus 3z, negative 1x plus 0y plus 1z. Like, do you see where these numbers came from in the matrix? They're the coefficients.
Yeah.
Like, that's kind of where matrices are traditionally introduced. But there's a huge connection between matrices and vectors. And one of these is in the cross product, okay? So this is a 3x3 matrix. Well, there are different things that you can do to matrices. You can do, like if I called this matrix A, you could do A transpose. Like A transpose is like where I put a little T there. And a transpose of a matrix is just you interchange the rows and the columns. Like that's A transpose. Does that make sense?
Yeah.
Okay. There are things called inverse matrices where I could find the inverse of this matrix, so that if I multiplied this matrix by its inverse, I would get the identity matrix. The identity matrix for a 3x3 is this. It's a matrix with zeros everywhere except for ones along the diagonal. Okay, so I'm giving you a crash course in matrices here, but it's not. You don't have to necessarily know all this right now. So you could take the transpose, you could find the inverse. Well, another thing that you can do to a matrix is something called the determinant. And what the determinant is symbolically is you put absolute values around it. Whoops. Like that. If you put absolute value bars around it, that's how you kind of denote you're taking the determinant of that matrix. And it turns out the determinant of a matrix is just a number. And it also turns out that this is actually what we call a metric function, meaning that this is measuring a distance, which maybe when Kate comes back, maybe we'll talk about this, because this is kind of an interesting thing, and maybe we could get into some of that linear algebra. But if you take the determinant of a matrix, you're actually going to compute a number, whereas all these other commands, these other functions were matrices. How you compute the determinant, there's a million ways to calculate a determinant of a 3x3 matrix, but it's pretty simple. You take a row or a column. So I'm going to choose this row because that's kind of how we're going to do it with the cross product. And then you take that column, or I'm sorry, that row, whatever you picked, and then I put the first entry right there as a 1. Can you guys see that? Or I'm standing in front of it.
Yeah, we can.
Then, next to that, I'm going to imaginarily, in my head, cross out that row and that column that 1 is in. And so then I'm left with 1, 3, 0, 1. Okay? And then I'm going to put that inside a little determinant. Then I'm going to go to the next entry, but I put a minus here. And then I imaginarily cross out that row and that column, so I'm going to left with 2, 3, negative 1, 1. And then I'm going to do plus, and then 3, and then what's going to go here?
2, 1, negative 1, 0.
Right. So that's all like fine and good. Now what do I do here? This is simple.
Do the same thing again.
No.
Oh.
Here, once you got it down to a 2x2, you just do this. 1 times, and then you just go this times this minus this times this. So it'll be 1 times 1 minus 0 times 3. And then you're going to do minus 2, and then it'll be 2 times 1. You just multiply the diagonals and subtract. 2 times 1 minus negative 1 times 3. Plus 3, 2 times 0 minus negative 1 times 1. And then you do this arithmetic. 1 times 1 minus 0 is 1. Minus 2 minus minus plus 3. 2 times 3, 2 plus 3 is 5. So 2 times 5 is 10. Right? And then what's going to go here?
0. minus 0, so it's just 0.
Well, 0 minus 0?
1.
Right? Or is that
No.
another negative 1?
Isn't that 0,
-1.
0 plus 1?
It's 1, yeah.
So this will just be 3 times 1 is 3. So that's 1 minus 10 plus 3, which is
-6.
-6. Okay. Now, I'm not ready to go over here yet, because I think you got to practice calculating a determinant. So why don't you just, for funsies, just on your paper, calculate this determinant.
Oh boy.
Actually, let's make it easy. Kate's probably sitting when she's going to watch this video, she's like, why is he teaching how to do this? If they just do A1, A2, B2, B3, like, because she's got the formula memorized. Calculate that determinant. And there is a way you can calculate determinants on your calculator. I can show you that later, though. It's not going to help you for doing a cross product, so.
Wait, so is it always minus the second one and plus the third one?
Yes.
Okay.
And if it was a 4x4, it would be minus, plus, plus, minus, plus, you know, you do that all the way. But you'll not have to calculate a 4x4 with me. Now you made me lose my train of thought.
Good, I can try to catch up.
You derailed me.
You're very easy to derail your train of thought.
Yeah, I know.
You can just talk about fishing, and then
I wouldn't say that's one of my better qualities.
That's fair.
Wow, it's amazing how I haven't done arithmetic in a while.
Feel that?
Did you guys get 10?
2.
But you got 10. More likely I would.
Well, check me. You derailed me, so I had to put the train back on the tracks.
So it's 3 times 4 minus 2 times 1.
Yeah, I got it.
Oh no. Okay.
Yay.
Now, interestingly enough here, friends, that the answer that we got for this 10 would have been the same answer had we computed the determinant and done it based off of that row. And then we did the same thing. Instead of having 1, 1, 1 there, we would have -1, 3, and 1. And then did the same, we would have gotten the same number no matter which row or which column that we did this with.
Well, yeah.
Okay? Now, when we compute... What? What's the matter, Wally?
What? I just said, well, yeah.
Oh, okay. Now, when we compute these determinants in the context of doing a cross product, you're always going to use the top row. Because if you notice the way I wrote this is I, J, K. Those are the unit vectors, okay? So, now... Now.
On letter time.
Now, when I go to compute this, it's going to equal I hat times A2B3 minus A3B2. You guys see that? Because if I imaginarily cross out these two things, I'm left with this times this minus this times this. Right? Then minus j hat times what? A1B3 minus B1A3 or A3B1. I'm running out of room, so my final component is going to be plus k hat times what?
Oh, you put a hat on the K? I didn't realize that. I didn't know that. I didn't know that was a thing. It's just new to me.
You just put them on I and J and left it. I mean, you just said.
I didn't even put them on I and J in the beginning.
Oh.
Yeah.
Well, I didn't up here. I probably because I could have.
Yeah. Come on, later.
So this is going to be A1B2 minus A2B1.
Oh yeah.
Okay. So these right here, boys and girls, these are the components, the X, Y, Z components of the cross product. Okay? Now, Kate, in her physics class last year, Mr. McManus just teaches you this formula and you just sort of memorize it. I mean, it's pretty easy to,
I was going to say, it's not hard.
you know, because you have 2, 3, 3, 2, 1, 3, 3, 1, 1, 2, 2, 1. Like, I just never did that. I just do it by computing the determinant in my head. So, and then you can also see what would happen if I switched these around, right? If I switch these around, B cross A, this...
All these would be leading instead of the A.
Right, right.
Yeah, B2A.
So it's going to cause these, to flip, and then it'll be the opposite. Like, it'll be the same numbers together, but it'll be the opposites. In IJK, the components will be the same, but they'll all be opposites. Okay?
Exactly the same, but opposite.
Exactly. All right, so let's just practice. Like, I'm going to give you a couple vectors. That's French for practice.
Le practice.
I'm going to keep these numbers small just because you have to do a lot of mental arithmetic here. So compute for me the cross product. A cross B.
Put the hats on better.
I don't have to.
You gave him crap for not doing it.
No, I gave him crap because I thought he was saying that he put them on I and J, but not K. Like, why would you do that? Like, that doesn't make any sense.
So either put them on all three or on none of them.
Well, it's probably good practice to put them on when you're actually writing them as vectors, but I'm not gonna I won't judge you too harshly.
Okay. Okay, I appreciate it.
You guys do this without me, and then we'll hopefully get the right answer. Or the same answer.
Okay. You're right.
Is that what you got?
Yeah.
I will tell you that if you're going to do this using the determinant method and not memorize a formula, like me, you got to remember this minus j. Like Joe, you asked me about that a second ago. Does it go minus then plus the next one? You just got to remember that. That'll be the common error if you don't remember, especially when you start doing these in your head and you start like adding and subtracting, or subtracting negative numbers and adding positive numbers or whatever. It's easy to forget that minus j. You'll all probably do it at one time or another, except Kate, because she's been doing cross products for centuries. You want to do another one, or do you feel good about that?
I feel pretty good.
Sounds good. We can do another one for fun if you want. Actually, no, I don't have room on the paper.
Yeah.
Okay, so make sure we okay, what is this number? Or I'm sorry, what is this vector? It's a vector that's perpendicular to this one and this one.
Oh, yeah.
Okay? Like if you took this and you dotted it with that, what are you going to get?
You're gonna get 0.
0. And if you took this and you dotted it with this, what are you going to get?
You get 0.
You're going to get 0.
Dot product.
Dot product,
The
yeah.
verb for dot product is dotted.
Yes.
Got it.
Or if you dot this with A and you dot this with B.
Too late.
Okay, some interesting geometry.
Interesting geometry.
Some interesting geometry. So we all agree that this right here, if this is the ta,
The ta.
that length right there is the magnitude of A times the sine of theta, correct?
Yeah.
So now I've got a parallelogram there,
Parallelogram.
and the area of this parallelogram is the magnitude of B, the base, times the height, yeah?
Yup. Yeah.
Well, kids, it turns out that these right here, now typically we'll put A first. That is equal to the magnitude of the cross product. So it's very similar to the dot product. Okay? Remember the dot product, if we said A dot B equaled the magnitude of A, magnitude of B, cosine of theta, right?
Yeah.
Like the value of the dot product was equal to that. Well, it turns out the magnitude of A times the magnitude of B times the sine of theta, this is a number. This is a scalar quantity right here. It turns out that it's the magnitude of the cross product. Okay? I'm going to skip the proof of this for right now. Okay? I'd like to maybe go back and do that later. Okay, but it is crucial that we understand that the area of this parallelogram that's made up by the vectors A and B, that the area of that parallelogram is actually equal to the magnitude of A cross B. Okay? That is a very, very crucial thing that's going to come back for us at the end of the year when we start talking about integration of vector quantities. Okay? So what do we know about the cross product properties? Can you guys see that okay?
Yeah.
Yeah.
Like, I mean, it's amazing how small I can actually write. I'm so used to writing huge so that everyone can see it, but I feel like this is tiny. Like, okay, so we already said that the cross product is not commutative. Like A cross B doesn't equal B cross A. It equals the opposite. Okay? But there are distributive properties that work. Like, let's say I say vector U, and I'm going to cross that with two vectors that I'm adding together. This distributes over addition. So that's going to equal U cross A plus U cross B. You see what I mean by it distributes over addition?
Yeah.
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 Oakley dokley. What if we have a scalar and we multiply it by A cross B?
Is that the same as CA cross CB? Does it distribute like that?
Well, yes, but it's going to do this first. You only need to distribute it once, if that makes sense.
Oh.
Like, 5 times 4 times 3 equals, it's like sort of 5 times 4 and then times 3, or it's
Yeah.
4 times 5 times 3. So if we don't parenthesize that, you can. Or you could be like, oh, well, that's equal to A cross CB. Okay? So you make sure you understand here that C is a scalar. What happens if you take a vector A and you cross it with the 0 vector? What are you going to get?
You get 0.
Well, you get the 0 vector. Now this one's going to be kind of weird. What happens if you take a vector and you cross it with itself?
You get a plane.
Oh.
What happens if you take a vector and you cross it with itself? Oh, that looks delicious. Did you guys know Joe was eating pizza this whole time?
Joe, you
No.
eat pizza.
Wow.
Mm-hmm.
I'm so jealous.
What kind of pizza is that?
Rapid fire from yesterday.
Ooh, rapid fire.
And cold pizza is the best pizza.
Well, I'm not sure if I agree with that, but
I don't disagree. Cold pizza's honestly good.
I mean, cold pizza's good. I'm not gonna diss cold pizza, but I'm not gonna say it's the best pizza. I think I could get on board with that statement.
Good.
I like the thin crust.
I like the thick crust.
I mean, honestly, though, it really depends on my mood.
That's fair. I think that's fair.
What happens if you take a vector and you cross it with itself?
You get a plane.
No.
You never said that.
Think about algebraically what's going to happen.
You get itself.
What's going to happen algebraically inside that determinant when you write out those components? Like you're going to have I, J, K, A1, A2, A3, A1, A2, A3.
Oh, they'll all cancel out.
Right. You're going to get 0.
Yeah.
The 0 vector. Okay, so what if I have a third U dot A cross B? First of all, the answer to number 6, is it going to be a vector or a scalar?
A scalar.
Very good, because what you're going to end up here with is a dot product. You're going to take 2 vectors, you're going to cross them, and then you're going to dot them with a third vector. Okay? Well, it turns out that it doesn't matter which order you do this in. You could be like, oh, this is equal to U cross A dot B. And this has a spatial name. It's called the triple scalar product. And it turns out that there's some interesting geometry of the triple scalar product. Interesting, maybe not so much useful, but it turns out that, let's say I'll got a vector U. And I got a third vector, another vector here. It's going to be vector A. And now I've got a third vector here. That's going to be vector B. Okay, so you got those three vectors. Well, if I do some
You're quite the artist.
Sometimes these are quite impressive drawings he makes.
Yeah. Mine do not look like that.
let's just do this. Okay. You get this. Oh, that actually doesn't look very good on screen. This back half is really offensive. I'm gonna fix it. Yeah, that's garbage. Embarrassing. It's a disgrace. You get this three-dimensional box, and this has a really fun word. It has a really fun name.
Parallelepiped.
Parallelepiped.
Parallelepiped. Yeah, that makes more sense.
It turns out that the triple scalar product is the volume of that parallelepiped. It's just kind of neat. I'm not sure how useful that is. I don't feel like we use that a whole lot, but it's kind of neat. What time is it? 1:40. What time is this class over?
55.
Oh, we got 15 minutes. Okay. Shall we do some examples?
No, I was drawing that. Dang it.
Oh, you want to? Oh, you want me to draw another one?
No, it's okay. I think I got one.
I could ask to see your drawings, but that might be embarrassing.
Mine is
It's not that
okay.
bad.
I know we've done this before in here, like, it's sort of like a contest of who can draw the best parallelepiped. Put that on your college application.